Alright, in this lecture we're going to continue our discussion on impedance, but we're going to spend perhaps most of this lecture time reviewing and trying to clarify again the big idea with impedance before we dive in and actually apply it to solving a number of circuits. So first, the big idea here. The big idea is we're studying systems, right? We're studying a system. Particularly, we're studying a linear system, and I'll be a little more specific, linear constant coefficient systems. All right, sounds maybe fancy, but all that means is not only is this circuit linear, but like our resistors, they're constant. They're not changing in time. Our capacitors are not changing in time. All right, so just trying to be a little more specific as to the class of circuits that we're studying. So in this, we're studying circuits, but it could be, any other domain as well, mechanical or whatnot. So we have some response. All right, and I'll say generally we have a response Y of t. All right, it might be a voltage or current, or it would be. And this is equal to, in general, a particular solution plus a homogeneous solution. Right? So this is steady state or forced. This is, we call it natural response or transient response. Okay, now this is true for any system, whether it's linear or not. There's always a particular and a forced response. But what is particular to the linear system is that the homogeneous response is always e to the st form. Always. Now we haven't proved that yet, or we won't actually prove it in this class, but we have seen it. We have observed it in the first order systems and the second order systems. And you could, if I wrote 5y triple dot plus 7y double dot minus 3y dot plus 8 is equal to 0. If you want to go through the work and try a e to the st, go ahead. You'll find that s can be found from solving for the roots of this characteristic equation here. Right? You'll have an S1, an S2, and an S3, and they'll all be used in the e to the st terms here. Right? So for a linear system, the natural response of a linear system is always e to the st. Then, what we're going to do is, let's say if I have some kind of excitation, so I'll say x going in. All right, so this is my excitation. We're going to discipline ourselves. We discipline ourselves to only excite the system with e to the st form signals of the form e to the st. Now we've seen before these would have several different forms. They'll be constant. This would be if s is equal to 0. It could be an exponentially decay. Right? That'd be s less than 0 in real. It could be exponentially rising in theory. And then we also can have complex exponentials, okay, which have this real and complex form. So it could be if we had s was equal to I'll say I'll just call it a plus j omega for right now. Okay, then we would have cosine omega t plus j sine omega t, the whole thing e to the at. Right? So we can have all of those types of signals for excitation. But what we do is we discipline ourselves to stay within this e to the st domain. And we know that the homogeneous response is always e to the st. So therefore, all signals in these systems are always of the form e to the st. Whether homogeneous, particular, or complete, or therefore complete. Okay, so we have so disciplined ourselves to a class of a problem that the only types of signals we're dealing with are e to the st signals. Therefore, we can, we'll say, pre-calculate our derivatives and integrals associated with our energy storage elements. All right, what do I mean? We're talking about the capacitor and the inductor. So, for example, we have capacitor current, capacitor voltage. We know that Vc is equal to 1 over C integral, integral IC dt. Alright, and we know that for the inductor we have IL and VL, so VL is equal to L dIL dt. Now, up until this point, when we were writing differential equations, we had to leave the integral or the derivative form as an expression to be used in our equations of motion, our KVL or our KCL. Because we didn't know what IC or what IL, what form they were going to be. So we couldn't go ahead and take the integral or take the derivative. But see now, because we have disciplined ourselves to work only with e to the st signals, we can go ahead and pre-evaluate the integrals and the derivatives. So since IC is always of the form e to the st, therefore evaluate the integral. Right, so we can say Vc is equal to 1 over C integral, we'll say A, some constant e to the st dt, and that simply pulls out the s, and we get A e to the st again, which is simply IC. So therefore we have Vc is equal to 1 over SC IC, right, as we evaluated before. And similarly, we have, since IL is always of the form A e to the st, therefore evaluate the derivative, right, as VL equal to L d dt of A e to the st, and that simply is SL times IL. Right. So that's, I know I've already said this, but I'm saying it again just to try to reiterate the big picture. We're not doing anything magical here. We've gotten so specific in the types of signals that we're using that we can go ahead and evaluate the integral and evaluate the derivative that are associated with these two energy elements. And now we can write this proportional expression or term that relates capacitor current to voltage or inductor current to voltage. And this is what we call, right, the impedance of our capacitor or the impedance of our inductor. Okay, so now let's put this to use in a general way, okay? So we'll put ZS to use in solving for the natural response of a two-port network. Of course, it's going to be more general than this, but and you'll see what I mean here shortly. Two-port network is just, I've got some linear network. It has, I'm sorry, I shouldn't call it two. It's a one-port. It's a one-port network. Two-port network would mean it'd have something on the other end, terminals coming in and going out. This is a one-port network, right? I've got one port, two terminals there. Right, so for instance, it could be something like this, as an example. I could have a resistor R, and then I could have a capacitor and an inductor in parallel. Right, and this could be inside this box, and I'll call this a one-port network. So it's nothing foreign to you. We just haven't been using the term regularly. Okay. Incidentally, if I had something like this, right, and I put a box around it like that, now I've got a port on the left and a port on the right. This is called a two-port network. Right. These are just very common forms, and so we give them these names. So I'm going to excite this one-port network with a voltage Vs. Okay, and I'm going to represent this one port by writing Z sub S, meaning when you look in to this one port, you see an impedance Zs. Now, let's look at our example here. What would Zs be in this case? Zs would be equal to R in series with a parallel combination of the impedance of a capacitor and the impedance of an inductor. So let's work that out. We have 1 over SC in parallel with SL, which is 1 over SC times SL over 1 over SC plus SL. And then we are going to, let's multiply through top and bottom by SC. So we'll have SL over 1 plus S squared LC. And then we might as well put it over a common denominator. So we'll have R plus S squared LCR plus SL all over 1 plus S squared LC. And I want to clean this up. By now you know this common form, right? For second order, I see that at the top I have a S squared and an S to the 0. There's R on the left. There's no, it's R times S to the 0. So I see this as a second order form. Let me put it into the standard. You remember our standard form, S squared plus 2 alpha S plus 1, right? I'd like to get it into that form, so I want to divide through the top and bottom by LCR, right? So I can get an S squared by itself. So I get S squared plus, when I take SL and I divide it by LCR, I'm going to have 1 over RCS, and then I'll have R over LCR, which gives me 1 over LC, and this is starting to look very, familiar. I have 1 plus, and then because, I guess let me put the LCR out here, right? And then, actually what I want to do, let me go ahead and divide the bottom, the denominator, by LC as well. So that gives me LC here, and that crosses these guys out. So let's rewrite this one last time. Z sub s is equal to R times s squared plus 1 over RC times s plus 1 over LC divided by s squared plus 1 over LC. Now you notice that much of the work in this is not writing the very first expression here. I mean, that's a critical first step. But to gain insight, and you'll see this in a few minutes because we're going to use this impedance, but to gain insight into what's going on, you have to do some of the algebra that takes you from the original form down to something that is more of a standard form. And then you'll be able to spot, if you're looking for ultimately s values, to find out the e to the st, the form, the functional form of the voltage or current response, you'll want to have the impedance in a more standard form. So take some time and look over what I've done here. The thing to guide you is that we want to put things into a standard form if possible. What I mean by standard is something is the s squared plus 2 alpha s plus 1. Okay, so back to our general problem here. I have this one-port network. I've applied a voltage Vs across it, and what I'm interested in is the current I. Okay, find, and specifically find the natural current response. Okay, and we'll call it IH. That's what we're after. We want to use impedance to do that. So, turn Vs off. In other words, Vs is equal to 0. So I have this situation where this is shorted, and I'm asking, what is this current? Okay, and the voltage here, of course, is 0. So just by Ohm's law, I have Vs is equal to Zs times I. Right? But Vs is forced to 0 because I've shorted it. Right? So what I find is that if there is any current that flows, if there is any possible current that could flow, when there is no external excitation, it must be such that that its value of S, or values of S, produce an impedance, Z sub S, that is actually equal to 0. So we would say, therefore, the only way that we can satisfy this, well, two ways. I could be 0, but the other way would be that Zs is equal to 0. Okay, so then the roots are the natural current response. Okay, so in other words, the zeros of Z of S give us the natural current response at the input of a one-port network. Sounds fancy, but it's just the appropriate way to express this. All right, this is a big idea here. So the zeros of Z sub S give us the natural current response. So for example, if I wanted to find the natural current response for the above network, this example here, all right, then I'm going to look for the zeros of the numerator of Z of S, right? if z of s is equal to some numerator, I'll say n of s, divided by some denominator, d of s, right? Then to find the zeros of z of s, I just need to find the zeros of the numerator. So in the above example, we have n of s is what? Equal to, well, I've got an r, but that's going to prove to be immaterial here. S squared plus 1 over RCS plus 1 over LC. This must be equal to 0. Well, I can recognize this. This is S squared plus 2 alpha S plus omega n squared. That's that standard form, where alpha is equal to 1 over 2 RC, and omega n is equal to 1 over square root of LC. So right away, I'm able to write these roots here. I'll say minus alpha plus or minus, and if it's underdamped, let's assume it's underdamped, then it'd be plus or minus j omega d, where omega d, of course, is equal to square root of omega n squared minus alpha squared. This would be if alpha is less than omega n, which we don't know. We don't have values here, but let's assume that it is. Right? You know this. It's just the method that by which we actually arrived at this. Now look at the circuit. The circuit is, let's consider the circuit. Alright, the circuit is simply this. R, capacitor and inductor in parallel, and now we're going to short the input. Right? This whole thing is just simply a parallel RLC circuit. Alright, and you've written the differential equation on the last homework and found the natural response, I think, for it. You certainly calculated alpha to be 1 over 2 RC. And here we have it. But we never had to write a differential equation. We actually did it by using impedance. Now suppose, on the other hand, that we forced, or that we excited Z of S, our one port, with a current source, IS. Alright, so that's the other scenario. We have two different cases here. When you've got a one port and you're going to connect some external excitation, you're either going to connect the voltage source or a current source. So let's try a current source. The response now is this voltage across the input. And we want to find the natural voltage response. Okay, not current response like before. Natural voltage response, V of H. Okay, well, when we turn this off, we're going to actually have an open, right? Nothing's going to flow. We'll have this voltage, but we'll have zero current. And we can write that V, or VH, I guess I should write, is equal to Z times I, but that's equal to Z times 0, right? Or we could write it this way: I is equal to 1 over Z times VH. Or in other words, it's equal to Y. Remember the admittance, which is 1 over Z, just like inductance, G is 1 over R, the resistance. Okay? So we have 0 current, right? By definition, because we're turning off the current source, is equal to 1 over Z times VH, or equal to Y times VH. So therefore, we have to find the zeros of Y of S, or we can call, or equivalently, we can say the poles of Z of S. In other words, when Z of S blows up to infinity. And again, just to be clear, I think this piece here is that this is maybe one of the trickier points. All we're saying is that we set up this network such that we disconnect the input. There's no current flowing. And we're asking the question, could there be a voltage? Could there be a voltage that exists across this one port when there is zero current flowing? And we answer, well, there could be. There could be, but if there is, but there may or may not, but whatever, well, there'll be a voltage. It could be zero. But whatever that voltage is, it has to satisfy impedance times current. Just like voltage has to satisfy R times current for a resistor in this case, it has to satisfy Z times I. But because I is equal to 0, the only way that you could have a non-zero voltage would be if Z were infinite, right? Or the admittance would be 0. And so you go looking for a value of S that would actually cause the Z to be infinite or the admittance to be 0. And if you find a value of S, or two values of S, or n values of S that do produce an infinite value for Z or a 0 value for Y, the admittance, then we say, aha, we have found a particular form of voltage that, if it exists, can do so while also maintaining zero current flowing through the input. And of course that's the only kind of current that would be possible, because the input is disconnected from any non-zero current source. Okay, so we can say, we can make a general statement here for the case where we're looking for the voltage response, or natural voltage response. We'd say the poles, okay, the poles of Z of S give us the natural voltage response at the input of a one-port network. Okay, the poles of Z sub S give us the natural voltage response. So here we have this poles and voltage, okay, and previously we had zeros and current. And think of it, if we're talking about impedance, then for there to be a current, think of there having to be like infinite conductivity, right? So think of the impedance being 0. And if there's going to be a voltage across some impedance, then isn't that most easily done when the impedance is infinite, which means there's a pole there. So that might be helpful in keeping these straight. All right. So this is our two big takeaways, that we can use impedance to find the natural current response or voltage response at the input of a one-port network. Now, in the next section, we're going to apply this to working some problems. Actually, I forgot. Let's continue our example that we had on the previous page. All right. So if we want to find the natural voltage response to this one port, then we're looking for the poles of the impedance or the zeros of the admittance. So let me just go ahead and write, since we're on to a new page here, let me write the impedance again. S squared plus 1 over RCS plus 1 over LC divided by S squared plus 1 over LC. Recall this is it's a numerator over denominator. So what I'm looking for is, if I want Z of S to blow up, then I need the denominator to go to 0. So find the zeros of the denominator. All right, what is the denominator? D of S here is simply S squared plus LC, and that's going to be equal to 0. Well, the roots to that are pretty simple. It's going to be minus plus and minus j omega n, where omega n is equal to 1 over square root of LC. Okay, now look at the network. Here's the network that we have, and this will make perfect sense. We have this network, and I'm drawing a box around it, and I'm connecting nothing to here, so we have zero current. Now look at this. If there's zero current flowing through the input, then this resistance has no bearing, right? It's not in the circuit. No current's flowing there. The only active circuit is this right here. In other words, the only circuit that can really have any current flow. It's the parallel LC. This is just a LC. I mean, is it parallel or is it series? Well, it's both, right? It's an undamped LC network. I mean, not underdamped, I mean totally undamped. And that's what this provides. It would say it's going to be sinusoidal at omega n forever and ever and ever. Right? So here we have used the impedance function, looking at the zero of the impedance function and the zeros of the impedance function and the poles of the impedance function to find the natural current response when we short this network, and the natural voltage response when we open up this one-port network.